because I'm a personal believer that radar is probably the best tactical tool a spotter could use. You know, 4, 5, 6 years ago or 7 years ago, before we had the smartphones, we used to teach these spotter classes, and we'd have to tell you, well, yeah, you got to have a laptop, and you're out there spotting to get radar, and then you got to hope to have some type of internet service, and good luck trying to get that. Well, things have really changed over the last 7, 8 years, because now, with people having the smartphones, just about all our spotters, law enforcement and the firefighters and emergency management agency, amateur radio operators, anybody that's out there spotting has a smartphone and has capability of having the radar right there on their smartphone. So this is a fantastic tool to use, and I think it's actually going to save lives, the increase of radar usage when we're out there spotting. And so this isn't your typical spotter class. I'm not going to be showing a whole lot of cloud stuff or anything like that. We're really going to focus in on the radar aspect of this training. And, you know, most of you that are from around here, if you've ever been out to the airports just down the road here, that's what our radar looks like. And that's what it's always looked like. But fortunately for us, we've been able to upgrade the technology of that radar. It doesn't make the radar look any different, but the innards and the software side of the radar actually has been upgraded with time, several different upgrades. Now, our radar, you know, we got one here in Springfield, but we've got many more radars, the National Weather Service network here, all across the country. We've actually got about 122 offices and more radars to go along with those offices. You know, we've got surrounding radars, Fort Smith, Arkansas, Little Rock, Tulsa, up towards Wichita, Topeka, Kansas City, Paducah, St. Louis, and Memphis. We actually dial into those radars because those are our surrounding radars, so we can locally dial into those as those storms are approaching from the west or whatever direction we're talking about here. Now, the radar, it's pretty simple the way this works. You know, we get a thunderstorm that develops, and what happens is we start to see precipitation fall out of the clouds, and what happens is the radar will actually shoot a beam, a pulse of energy. It travels in a sine wave, and that pulse of energy, it'll start to interact with this precipitation, whether it be hail, heavy rain, light rain, whatever it is. That pulse of energy will reflect off of that precipitation, and some of that reflection will be reflected back to the radar. And the radar measures how much of that energy is actually reflected back to it. So as you can imagine, the heavier the rain or the larger the hail, the more energy is actually reflected back to the radar. And that's how we know if we're dealing with heavy rain, light rain, or maybe even some hail within that thunderstorm. So the type of analysis that you guys are probably used to seeing the most, or what you see on the TV or whatever, that's called reflectivity, because the radar is measuring how much reflectivity is brought back to it. So in this case, July 4th of 2004, we had this just incredible squall line that came through with 90 to 100 mile per hour winds. We actually had a 6-year-old girl that was killed up here at Quapaw, Oklahoma from this line of storms because of the straight line winds took out a large tree into a mobile home. And but that squall line here, as you guys know, the yellows and the reds within that's the highest energy return back to the radar. And so that's how we know that's the heaviest part of the thunderstorm. But these greens up there, the light greens and the blues, that would be low energy reflected to the radar. And keep in mind, this black spot right there, that's what we call the cone of silence. So that's the radar location just down the road here on Highway Double E when we're doing this type of analysis. Now, the second basic type of analysis that the radar performs for us by using the Doppler principle. If anybody's ever taken physics, you probably know what the Doppler effect is. And using the Doppler effect, we know what the velocity of these raindrops or the hail or the precipitation particles within the thunderstorms, how they're moving and what direction they're moving, and the speed of that movement as well. And this is what we call velocity. And the area that I'm most interested in is right here across eastern Webster County, where we've got these really bright pinks right next to the really bright blues and the bright greens. So the really bright pinks indicates winds very strong, 90 to 100 mile per hour, that are going away from the cone of silence or the radar location. Well, at the same time, we've got really strong winds, about 80 to a 90 mile per hour, going towards that radar. So what we have happening there, obviously, is a very strong rotation within that thunderstorm. And you know, back before we had what we call dual polarization, which we're going to talk about in this class, is groundbreaking science. That's all we had to go off of in diagnosing thunderstorms and their ability to actually produce tornadoes. So we're not seeing the tornado here, we're just seeing the rotation within that thunderstorm. Now, something that you may not know, the radar actually, it takes different cross sections of the atmosphere. So in this instance, what we do here is we shoot out a pulse of energy at this low elevation angle. This would be like the half-degree elevation angle. It makes a complete sweep around the atmosphere, and then once that sweep is done, it'll raise itself to the next elevation tilt. So this would be like a 1.5 degree. It makes that sweep, comes back around, and it just keeps going up. And this allows us to look at thunderstorms three-dimensionally. That's really important because when we're trying to assess whether or not a thunderstorm is severe, we've got to be able to look in the upper parts of the thunderstorm to see if we've got a hail spike or maybe some type of reflectivity value that would suggest there's hail up there where it's really, really cold in the atmosphere. So in this situation right here, we've got a thunderstorm that may develop like that. Notice that this y-axis is height above ground level. So this thunderstorm's top of it, this is very common, maybe between 50, 60,000 feet up above the Earth's surface. And if a hail core develops within the mid and upper portions of that thunderstorm, we won't be able to see it with this pulse of energy right here, nor this one, and nor this one. So these lowest three elevation tilts, we wouldn't be able to see that hail core. But because the radar continues to go up higher and sample thunderstorms within the mid and upper levels of that thunderstorm, it's these tilts, the 3.4 and the 4.3 tilts, is where we're going to see that hail core, and that's going to allow us to issue the severe thunderstorm warning if we think that hail is going to be 1 inch or larger. So it takes about 4 to 5 minutes to complete this entire volume scan. So from the half degree all the way up to the 19.5 degree slice, that takes about 4.5 to 5 minutes, depending on what strategy we're using. Yes, sir.
So according to the radar images we saw previous to this, that's a composite of all the layers put together?
No, sir. And that's a good question that you got there. What you're seeing right here with this squall line, that is just the half-degree slice.
That's the half.
Yes, sir. So this gentleman here mentioned composite, and I don't use composite. Matter of fact, when I'm assessing whether a storm is dangerous or not, I don't use composite imagery because it mucks up the features that I'm trying to look at. So the composite basically is going to take a combination of all of these elevation tilts. Okay, so it's going to take all of these together, and it's going to take the highest reflectivity value per tilt and then overlay that with each other.
And then the base one would be the...
Right. So as a warning meteorologist, I never use composite, and I don't recommend a spotter use composite either, because there's going to be like hook echoes and low-level reflectivity gradients, weak echo regions, and things like that you won't be able to see if you're using the composite. So yeah, that's not really something that we use. So in this instance right here, this is the Stockton supercell back on May 4th, 2003. You know, I worked this storm. This is one of the first tornado outbreaks that I worked when I got here to Springfield. You know, I issued a tornado warning on this thing on every single county that this hook echo touched, from Wichita's area all the way into St. Louis's area, and verified every single one of those tornadoes. This is the most incredible storm I've ever worked. It actually produced an F4 tornado in a town called Franklin, Kansas, and it's just north of Pittsburgh, Kansas. It's a suburb of Pittsburgh. And I'm not exaggerating when I say this, there was nothing left of that town. I mean, it was a small town as it was, but there was nothing left. There was nothing left standing in that town. So just an incredible storm. But this is when it was overstocked in here. And to kind of give you an idea about how this works and how we assess thunderstorms, this is just looking at the half-degree slice right here. So this is the very low levels of this thunderstorm. And we're sampling into this thunderstorm at right around 3,000 feet above the Earth's surface. So that's about as low as we can get for the northern part of Stockton Lake or the city of Stockton right there. And that low level is very important in assessing whether or not a thunderstorm is going to produce a tornado, because a lot of times in these supercell situations, we'll see that rotation way up high, but it's got to get down low before we're really concerned before that thing starts producing a tornado. So this was about 3,000 feet up. Now we're going to go another elevation tilt up. That's about 6,500 feet up above the Earth's surface. Then you can see it looks a little different. You've got a weak echo region right here. This is what we call a B-wave, a bounded weak echo region. And that's very common with tornadoes. And that's only a 1.5 degree slice. Now as I move up to the 2.5 degree slice, you can see it starts to look even more different, because we're shooting into the storm at about 10,000 feet up. So we're trying to get a three-dimensional visualization of what these thunderstorms look like. Yeah, looking at the low levels are important, but we've also got to look at those mid and upper levels, because there's some hazards up there, especially when it comes to microburst generation and hail generation. Yes, ma'am?
How tall do those thunderstorms get?
Yeah, you know, the tallest one that I probably ever worked was about 65,000 feet. Okay, so you know, that's up into the stratosphere basically. So you know, basically we've got the troposphere, and then when temperatures start warming back up, you know, at around, a lot of times it's probably right around 35,000 feet up. That's what we call a stratosphere. It's sticking way up there in the stratosphere. So. That's about 1,300 feet up, 14,000, I'm sorry, about 14,000 feet up there at the 3.5 degree slice. And when we start getting into the mid-levels of these types of thunderstorms, this is where I'm going to start looking for my microburst generation. And what we look for in that is when we look in the velocity of the mid-levels, we'll start to see some areas of convergence. And this is very typical in the summertime when we get the impulse thunderstorms where they're not really that organized, but what you will see is convergence in the mid-levels, and that's a signal that you're getting ready to have a downburst with some of these storms. Well, supercells like this often produce those. So those are some of the things that we're going to be looking at. Now, one of our thresholds we typically go by at the Weather Service is that we'll start to get severe hail when we start seeing the 55 dBz levels at around the -20 degree level. So we've got the capabilities at the Weather Service where we put up a radio sonde using a weather balloon, but we know what level that -20 degree level is. And then we'll go by that. If we start seeing updrafts that shoots above that level, that's a good indication that we're going to get 1-inch hail or larger within that particular storm. On this day, that -20 level was right around 19,500 feet. Well, we're sampling this thunderstorm right here at about 21,300 feet. So we know a large portion of this thunderstorm with 55 dBz right here is producing severe hail in this instance. So if we were to see that, punch that threshold there, that's when we're going to issue a severe thunderstorm for large hail. And then going all the way up into this thunderstorm, that's 7.5 degree slice. So we're looking at about 25,000 feet up there above Stockton. That's 30,000 feet. Okay, so and then we also have the capabilities of drawing up cross sections. So we can draw up a cross section using our ellipse computers out there. If you've ever been to the Weather Service, we'll draw up and slice and dice these thunderstorms, and we'll have analysis like this that gives us an idea of how high these thunderstorms are. So again, that's 10,000 feet, 20,000 feet, all the way to 60,000 feet above the Earth's surface. And then this is the reflectivity. So this kind of gives us a cross section or a profile of what that thunderstorm looks like. So on a day like that, when that -20 level degree was right around 19,000 feet up, you've got a large chunk of this thunderstorm that is capable of producing large hail, given this situation right here. So, any questions about cross sections or the vertical continuity of thunderstorms? That's really important. You know, a lot of people don't understand. They think that the radar just kind of scans the sky like this, but that's not the case. It scans the sky, but then it keeps going up in elevation tilts that allows us to visualize those thunderstorms three-dimensionally. Yes, sir.
I wanted to make a comment, a lot of people don't realize that the average height of a commercial flight is about 28,000 feet compared to the height of that storm.
Yeah. And that's why you see a lot of airlines go around those thunderstorms. So, yeah, you know, weather pilots are pretty weather savvy, and we've got we do aviation forecasts for 3 different airports here, Branson, and then Joplin. But we've also got a part of our agency called the Aviation Weather Center up in Kansas City, and they're constantly putting out like things like this, like SIGMETs and things like that, talk about turbulence and things to those pilots. Yes, sir.
You mentioned weather balloons. I mean, are you putting a weather balloon into this thing?
Not intentionally. We don't put weather balloons intentionally into thunderstorms. Really, what the weather balloons are is to generate what we call forecast models. So here at our office in Springfield, we'll put them up twice a day. So right now we're putting them up at 5 o'clock in the morning and at 5 at night. And when that weather balloon goes up, it almost goes pretty much to outer space, about 5 millibars. It's about 20 miles up above the Earth's surface. But it's got an instrument attached to that balloon that goes up, and that instrument, at every single layer of the atmosphere, it measures temperature, humidity, wind speed and direction, and pressure. And with all those 4 basic meteorological components, there's about 72 other offices across the United States that's doing that at the same time. And when we get that data, we send it to Washington, D.C., and those other offices do it at the same time, and they crunch all of that data into what we call a supercomputer. And those supercomputers takes 7 different primitive equations that explains how the atmosphere works. It takes that data into those equations, and that's how we get our forecast models. So those balloons are very important in generating your guys' forecasts. It's the backbone of weather.
Is that how you know where the jet stream's doing, how fast and all that?
You're exactly right. Yeah, because if the jet stream's right over us, that balloon will sample that, and we know how fast those wind speeds are at the jet stream level. Yes, sir.
How fast does it take to do a sweep on the radar?
That's a good question. It's 4.5 to 5 minutes. So that's what we call a volume scan. So an actual sweep is pretty quick, but as I just illustrated, it'll do a sweep, but then it'll go up an elevation angle sweep, elevation angle sweep. And so once it gets all the way up and it finishes that 19.5 degree slice, that's what we call entire volume scan. That takes about 4.5 to 5 minutes. Now that really depends on the radar strategy that we're using. There's some strategies that may skip some of them elevation angles, and some of them do all of the elevation angles. The ones that skip go a little bit faster. The ones that do all of them, it's a little bit slower. So we've got about 6, 7 different strategies that we can use. The one that we use the most for we get into like a severe weather situation or a tornado outbreak is going to be what we call VCP, Volume Coverage Pattern 212, so 212. That's the best one for tornadoes. All right, so you know, in this situation here, this is another way we analyze storms. We've got ability here to use 4 different panels at the same time on our screen, and then we can overlay the velocity on each one of these panels. So in this situation here, I'm looking at the lowest parts of the thunderstorm, and then I'm getting into the mid-levels of the thunderstorm, and then more of the upper levels of the thunderstorm over here in this 4th quadrant. So you can see when you overlay these all together and you're looking at them, you can get a good idea about what the structure of the thunderstorm looks like. Nice hook echo. This was March 12, 2006. Storm that went into Branson, and if some of you guys remember, that night Branson had hail about this deep, and that was this very thunderstorm. We thought this was going to be the Branson tornado, And because it had a tornado back here in northwest Arkansas, but it lifted by the time it got in Greene and just produced a bunch of hail. Well, what's interesting about this thunderstorm is you can see what we call this little spike area right here, and you can see it here coming out of that storm, and you can actually see it a little bit up here. That's what we call a hail spike. And so when we start seeing these hail spikes, we know that, well, there's a 100% chance the storm has hail. Now, will it make it to the ground? So that we have to kind of figure that out as well. The other thing I wanted to point out to you is, notice this donut hole right here in the middle, it's parts of the thunderstorm. Again, that's what we call a bounded weak echo region. That's indicative of a thunderstorm that has just a very strong updraft. So, thunderstorms have updrafts, they have downdrafts. Well, this type of thunderstorm is so organized, it was so unstable that day. That updraft was actually punching a donut hole right in the middle of that storm. We know we got storms that's got major updrafts like that. The probability of a tornado occurrence really starts to go up. So these are things that we look at when we're diagnosing whether or not we need to issue a tornado warning. And then this spike right here is something that we look at to diagnose severe thunderstorm warnings for hail. So in this situation right here, you notice that we've got almost a donut hole in the lowest part of it because we've got this hook echo coming around. And again, that's what we call a weak echo region or a weir. And you can kind of see that there. It's not closed off, so it's not bounded yet, a weak echo region. But right here, it's completely closed off into that donut hole formation. And that's what we call beware, so the bounded weak echo region. Now, some of you that may be on National Weather Service chat, we got a gentleman right here from KJL here tonight with the Lebanon Media. He's on our chat, and he's always talking to us all the time. So when we talk about this terminology on chat, we'll talk about bewares and weirs, and that's exactly what we're talking about here. These are very important features in determining whether or not a thunderstorm is going to be dangerous. And here you can see another identification of a hail spike in this situation right here. And a hail spike is generated because when that pulse of energy goes out and it hits big hail like that, some of that energy is actually reflected downward to the surface of the earth. Okay? Well, then it gets reflected off the surface of the earth back into the hail, and then it reflects off the hail again and goes back to the radar.
So you're saying that hail spike is not sticking out the south end of the storm, it's just the weird,
Yeah,
the way the echo's been.
it's a fake echo, but it's reflected. It's called a three-body scatter spike because it was reflected 3 times before it got back to the radar. So that's the physics behind that. Very, very interesting phenomenon that we have. Here's a big 3-body scatter spike right here. So it's not really, like you said, it's not hailing right here. It's not even raining right there. It's a fake echo caused by hail within this thunderstorm right here. But the radar thinks it's positioned right here.
Now, is your radar the only one that picked that up, or would we pick that up like on our little apps?
Oh, you'll pick it up on your apps. I use an app called WeatherScope, and I find that was the best one because with WeatherScope, it's got all the updated technology that the radar has, including dual polarization, and it's got the best format that looks closest to what I use at the National Weather Service in assessing the danger of thunderstorms. So that's why there's a lot of them out there, but I use radar scopes.
But still, they're basically the same. You just gotta look at the graph or the legend to see whether it's coming to you, going from you, or the intensity of it. There's still, what you're saying is pretty much generic to all the other apps, products that are out there.
Yeah, there are some apps that I have a hard time looking at, but some of them, my opinion, some of them are better than others. But the radar scope is just so close to our AWIPS monitors that we have and how it formulates the radar data that's what I like to use. That's what I'm most looking at work. So, but yeah, there are a lot of different apps out there. But yeah, 3-body scatter spike is what that is. A big hail, a lot of hail. You know, again, this is the same storm that produced that hail there in Branson during the March 12, 2006 tornado outbreak. So let's talk about rotation. You know, we use velocity within the thunderstorm, the Doppler principle, to look at rotation of the thunderstorm. That's really important because when we have a thunderstorm that's got rotation, that increases the probability of tornadoes. So rotation is very important to us. And in this structure right here, we're going to say that the radar is located south of these velocity, what we call velocity couplets. So the radar is south. And these blue colors indicates precipitation particles that are going towards this radar down here, and the red indicates precipitation particles that are going away from the radar. So let's look at the different velocity structures that we often see utilizing the radar, because a lot of this is kind of unknown as well. So in this situation, this would be pure rotation because we got a pure counterclockwise rotation here. So that would be good for tornadoes. So that wind field would look a lot like this here. You can see the arrows going, just a pure counterclockwise rotation. Now, in this situation here, we've got the radar located here, so we know that the blues indicate winds that are going towards the radar, and the reds indicate winds that are going away from the radar. So I'm going to ask you this, what is happening there?
Microburst.
You're exactly right. This is what we see when we hit microbursts during the summertime, especially in the summertime, July and August. You know, a microburst is just this column of air that comes down really fast and then it crashes to the ground, and then that air just kind of diverges like that. When we see something like this, we've already got a microburst in play, and hopefully we got a warning out. If we see it and we don't have a warning out, it's too late. We already missed it because the ground's causing that divergence. So yeah, that's a good pick up there. Now this is what we call convergent rotation. This is also a very dangerous indication of a tornado developing. When we have big tornadoes, we often have this type of signature right before that tornado develops, or right during the developing stages of the tornado. So notice that the rotation is not pure because it's kind of converging on each other. It's still rotating, but it's got a very strong convergent component to its structure there. So the wind field, you got a tornado and everything's just kind of converging on that rotation there. So this is a good one that we look at, a good structure for tornadoes. And this is a divergent rotation. And this is sometimes what we get when the tornado is actually beginning to dissipate or already has dissipated. So this is a less dangerous of an indication that a tornado is ongoing. We'll see that as well. So here's a good example of a couple of different right here. What would you say this is up here, just looking at this velocity couplet?
Where's the radar site?
The radar site is going to be over here. Yeah, southeast of that couplet there. So would you say that's convergent rotation or pure rotation, divergent rotation, or pure divergence?
Convergent.
Convergent rotation? Yeah, you're exactly right. So it's not pure rotation because the velocity max for the inbounds is up here. The velocity max for the outbounds is over here, so it's converging, but it's rotating at the same time. So yeah, I would call that a convergent rotation in that situation. And then up here, what about this one?
Divergent?
Pure rotation.
Yeah, pure rotation. That'd be a pure rotation. Yeah, we just call that rotation. And then this one here, down here, that again, that would just be pure rotation. Looking at that velocity. And same thing for this one over here in this fourth quadrant. That would also be pure rotation. Pulse thunderstorms, these are the July, August thunderstorms, about 95 degrees out. Got dew points in the mid-70s. It's just really humid. But the thing is that we just don't have a whole lot of wind flow that time of year. So these things just aren't very organized. You can see it looks like popcorn. They're just kind of developing at random, just kind of wherever. But these are the type of storms that we get those downbursts, like the gentleman said back there. Here's a good indication of a downburst that we had just north of Fair Grove, where we got, this is very interesting to me because we've got those greens. Here's the radar, kind of silence down here. So we got these greens going towards the radar and the reds going away from the radar. So when I saw that day, we already had a microburst in play. And we see these all over the place. Here's one south of Ash Grove. Can anybody pick it out? This is very noisy, but if you look in this area right here, you can see the greens indicating winds that are going towards the radar, and reds are going away. I missed this one when I was working this one too. We didn't have a warning out, and we ended up getting some trees down over there by the Lawrence Greene County line that day. That was a few years back. And anybody pick that one out? Yeah, another divergence signature right here. So again, this stuff's noisy, but we're trained to look for these things. The more radar you work, the more you understand how this stuff kind of looks. We also look for what we call storm top divergence. And so when a thunderstorm goes up, you got the updraft that's going up like this, and then often at the top of the storm it diverges out, especially if you've got a jet stream. Yeah, so yeah, the stronger that divergence, if you've got more air pulling away from it at the top, the more air that wants to come up to that, because it's basically like a vacuum. It's sweeping that air up. So you're exactly right. That also creates the anvil. And the stronger the storm top divergence, like in this situation here is, like if we start getting storm top divergence of 75 knots or more, then that storm has a very high likelihood of becoming severe, either creating that large hail or maybe some type of damaging wind. So this is about 40,000 feet above the Earth's surface. We got these yellows and these reds indicating the winds are going away from the radar. Bright blue is going towards the radar. We measured that out to be, I think it was about 75 to 100 miles per hour storm top divergence. So that's a good indicator for storms that are getting ready to become severe or that already are severe. All right. This is, in my opinion, probably some of the most important part of this talk, because I know a lot of you understand reflectivity very well, you understand the velocity very well, and you understand how the radar works. But in February of 2012, we installed a new technology called dual polarization. And it's incredible. We were training up on it several months, 8 months to 10 months in advance of getting this technology. And it wasn't until the Leap Day tornado outbreak is when I realized how significant this technology really is. Because many of you have been to the spotter talks in the past, and we always told you, you know what, the radar, it's a myth that the radar can see a tornado. We issue the tornado warnings based on the rotation. Well, the radar can see tornadoes now because of this upgraded technology. So it's very significant, and we do see the tornadoes. It's what we call a tornado debris signature, a TDS. Again, you're going to need to know that on NWS chat. Patty's also on NWS chat as well for you guys communicating that information. A tornado debris signature, a TDS. When we see one of these things, we know we are 100% confident that we've got either a tornado on the ground at that moment or a tornado has touchdown and the debris is just still in the air. So this is the radar's ability to see foreign objects such as sheet metal, roofing shingles, 2x4s. The radar's saying, uh-oh, this isn't raindrops. This isn't hail. It's not hydrometeors. This is a turkey barn, or it's turkeys, or something like that. So with this new technology, we are able to see tornadoes. Here's this is the very first one we saw. This was February 29th, 2012, 2 weeks after this new technology was installed into the radar. And we saw this, and everybody's eyes just went really wide in that office that night because we realized, oh gosh, this works. And we have a tornado. And for the first time ever, we are 100% confident in putting in our warning, a tornado is on the ground. It's moving into Buffalo. And this is going to save lives. This is groundbreaking science that will save lives. Now, I'm going to say, we're right in the midst of spotter talk season, and I've had the question, well, if we've got this technology, what's the point in having spotters? Okay.
See it before there's a debris field.
Yeah.
The problem is this is not perfect because this only works given certain situations. If you've got the radar beam that's overshooting that tornado, I'm not going to see it. Also, our job at the Weather Service is to get a tornado warning out before it actually occurs. So it's the wall cloud reports, the funnel cloud reports that we get from you guys is what's going to allow us to get those warnings out before the tornado actually occurs. This only works after the tornado has touched down and is doing damage. So yes, there is a very significant need for human spotters out there, and there always will be.
Well, in the radar in Springfield, the storms are too close for the radar here, so you don't see squat from like Halltown back past Springfield a little
Oh, I'm going to show you that you're wrong.
bit. Really?
I'm about to show you that. Okay, so this was the Buffalo. This is actually a line segment, not necessarily a supercell storm, but more of a line segment storm. So up here, we're familiar with the reflectivity. We're familiar with the velocity. We just talked a lot about those two. But these two panels right here, down below, that's the dual polarization. That's the new technology that most of us probably haven't quite seen yet. And what I want you to do is fixate your eyes right around here to the southwest of Buffalo, near that Polk County, Dallas County line on this very next volume scan. When we go to this next volume scan, boom, we see something light up here. It's this blue donut hole that lights up within this analysis. We saw that night and we were like, holy cow. Well, what happened was that tornado, it came down and it took out a turkey operation. So we had sheet metal and who knows what that was flying around in that tornado, and that our radar was actually able to see that tornado given that instance. So now I'm going to progress through the series of animation here to show you what these things look like. On this next volume scan, you can see how tight it is right here. This is the lowest teal, but this is the lowest teal, and this is the 0.9 degree teal. So this is the lowest. This is a little bit higher than that one from an elevation standpoint. Now, you can see how tight it is initially, but when I go through with time, what happens to it?
See the debris spreading in one direction.
You're exactly right. What's happening, the tornado's not necessarily getting bigger, but the tornado is throwing out debris in every single direction, and it makes the radar think that the tornado's wider than what it is. This is a very common process that we see as these tornadoes, they develop, it starts out narrow, and it gets wider because that debris is getting kicked out. It's about this time here, you can see it's even a little bit wider, but at this point, it's not on the ground anymore. So why are we still picking up the signal? Yeah, you still got debris that's floating around in the air. So I just got done training 2 months ago in January the TV meteorologists, and both here in Springfield. Every single one of them showed up to this training. And also the Joplin TV meteorologist, right about the week after that, talking about introducing them to this technology and what it means. This is a big part of it because in this situation right here, that tornado is not on the ground, and I had to explain to them that we can have this, and that doesn't give you a 100% chance that it's on the ground still. That means it gives you a 100% chance that a tornado happened, but it doesn't necessarily mean it's on the ground. So you can't see here, if this is over a town and say, hey, we are 100% confident this large tornado is going through Buffalo. We don't really know that for sure, but we do know that there's debris in the air and a tornado caused that. So Patty, that's something that when you're communicating with these guys,
Yeah.
we're going to tell you that on NWS chat.
Right.
You too there at KGL.
You're seeing this in the correlation coefficient, correct?
That's correct. That's what we call correlation coefficient. So it's a component of the dual polarization, is what that
So,
is.
so what you're saying is even though it's down up, people still got to be aware and go, oh, it's gone, it's cleared up, heads up, because what comes up, gonna come
Yeah, you still got debris floating up there. It's gonna come down. That's right. And this is exactly why.
You might want to put your helmet on, it might
Yeah.
be raining down.
This is exactly why we tell our spotters, don't get too close to these tornadoes because there's 2x4s and all kinds of stuff that's flying missiles. Most people get killed by tornadoes because the debris strikes them or maybe they get slammed to the ground. And so flying debris is a problem. This is why we get, job of tornado, and we get, pieces of mail and stuff like hundreds of miles away because it gets sucked up into the flow. Okay, so that kind of goes away there. Now, here's some more interesting stuff. A lot of this is always speculated. Now, I grew up on a farm in Kansas. And I can tell you sometimes, you got farmers out there, what the hell happened? My row of trees got mowed over. It looks like a tornado came through here. Well, it never gets reported back to the sheriff's office because we just didn't do that. We have storm damage. We don't report it to the sheriff's office or we don't call the National Weather Service. So we've always speculated that there's more tornadoes that actually occur than what's reported back to the office or what's documented in storm data. Well, guess what? The dual polarization is confirming that. And in this instance right here, this was in May, I think it was May 20th of 2013. This was the same storm that produced the Moore, Oklahoma F5. But by the time it got into southwest Missouri, it had evolved into a line segment, more of a squall line. And I was working this storm. I had tornado warnings out on the squall line back at Stone and Berry counties. But I didn't have a tornado warning for Taney County, and this is what happened just north of Walnut Shade. I want you to focus your attention there near Bull Creek on this next volume scan. Boom, there she popped up right in the middle of the woods. I never got any reports of damage, debris, or anything. As a matter of fact, we never even saw this until over a year later when we were going back and looking at the event. Okay, so yes, if you speculated there's more tornadoes that actually occur than what's documented, you are correct. And our radar is now confirming that. Dissipates and goes away. Now let me give you some statistics. So knowing that, what we did was we went back, okay, we installed this technology February 2012. We went back and looked at every single thunderstorm event that we had since this new technology was installed. We combed through it with a fine-tooth comb and to see what tornadoes and how many tornadoes were missing. How many of these things are actually popping up out in the woods that we never got. All right, so we calculated some stats. It's been pretty quiet since 2012. Seems like Joplin hit, we've been pretty quiet. We haven't had anything more than EF2s. Had a lot of EF0s, EF1s, and EF2s. We've had 37 tornadoes in our area altogether. All right, so the number of tornadoes in EF1s were 14. So we've had 14 EF0s. The number of TDSs that popped up with these 14 tornadoes were only 4. This is why we still need storm spotters. The stuff is not perfect. Under certain conditions, that radar is not going to see that debris. Especially if those tornadoes, small tornadoes, which are shallow in the first place, pop up long distances away from the radar because we're overshooting them. Okay? Still need spotters. This is not perfect. EF1s. Since February 2012, we've had 19 EF1 tornadoes that we've documented. We only had 4 TDSs that popped up with those 19. That's not a good, very good percentage. EF2s, we've had only 4 of those, and all 4 of those stronger tornadoes were signaled by the radar. So that's good news. You know, a lot more injuries and a lot more fatalities happen when tornadoes are EF2 or stronger. And the good news is we've got 100% detection with those bigger tornadoes. So that's a good thing. We had a couple of EF2s last year out in southeast Kansas, and we booked, and that's a long way away. Baxter Springs, Kansas, north of Fort Scott, EF2s out there, and we saw them. And that's a long way away, and we still saw them. Yes, sir.
I'm curious as far as your dust particles. It's not quite picking up the dust particles yet. It's got to be debris, right?
It's got to be debris.
Okay.
Okay, and here's the thing, because we wondered that too. Because I'm going to show you some stuff here.
There are areas, you know, this in the United States that have metallic in the soil. That's why I was wondering if it actually picks any of that up.
Yeah. We've had some squall lines where families of these things are popping up.
Okay.
And we were wondering, things like, are these really tornadoes? Because there's so many of them. And we took the data down to Norman, Oklahoma, to the Severe Storms Laboratory, to the Storms Prediction Center. And these guys, like Les Lemon, like the grandfather of radar, are saying, well, there's only one thing that could cause this. When you've got debris being shot up 9,000, 10,000 feet above the Earth's surface and it's in a circular form, it's got to be a tornado. There's only one weather phenomenon that can happen with it, and that's a tornado.
So-
Straight line winds is not going to send it 9,000 feet up.
So there could be more vortices popping up in the folding on the front end of those.
Yes, that's exactly what happened. Squall lines, after seeing this data and doing this study, I'm 100% confident we get more tornadoes with squall lines than we do with supercells. I'm going to show you a couple examples of those here in just a minute. So, after doing all that data, only 12 of the 37 documented tornadoes had a TDS. But unfortunately, what's even worse is that 15 TDSs showed up with no confirmed tornadoes. Meaning, after combing through the data, there were 15 tornadoes that we never got damage reports on. They happened out in the middle of the woods and rural areas that nobody reported to us. So there's a lot of tornadoes that happen that we don't know about. Now granted, it's going to be the small ones. The big ones, those are getting reported to us, I think. But the small ones, I think there's a lot of those that just aren't getting reported. Here's another example. This was also the same night Branson was hit, February 29th, 2012. This was an EF2. So this is one of the EF2s that we captured since we've had this technology. And I was working this storm, and I got lucky on this because, you know, I was working. See this Cook Echo right here. This was a very well-defined supercell. My focus was on that baby. You can see the rotation from it. Okay, nice rotation. When I issued the tornado warning for Berry and Stone counties, I decided to go ahead and extend it further north because if you look up here towards Cassville, there's some minor rotation with this squall line up here, this cluster. I was like, well, you know what? I'll just go ahead and cover it since it's there. But I would not have issued a tornado warning on that if it wasn't for the supercell. Well, I went ahead and covered it. And I want you to focus your attention up here, Cassville, and boom, what do you see? Right there. And so we saw this, and we're like, well, we got a tornado. And then we started getting fatalities from that. We had a couple fatalities from a mobile, there was 3 mobile homes that were just disintegrated from this. And I went down there, and there was a frame home right next to those mobile homes. And there were 2 people. There was a mom and like a 15-year-old boy, her son. They were in the bathroom, and that was the only thing. A center bathroom, a small room on the lowest floor, center section of that house. It's the only thing standing in that house. And they were in there and they survived. So, mobile homes, nothing left but those undercarriages, the frames, the black frames and undercarriages. So, that wasn't even associated with the Branson storm. That was just with this line segment up here. But this supercell down here, it did eventually go ahead and produce. Go ahead and show you this. So it started, here's Kimberling City, and we think this tornado started there in the main channel of the White River. So if you know Table Rock Lake really well, there's a confluence there south of the swings where the James River meets the White River. We think that tornado started right in there, or maybe just west of there on the main channel. And the reason why we think that is because right in here on this next volume scan, right above Kimberling City, you can see the indications of that tornado as it passed through Kimberling City. But in Joe Ball Peninsula, we had a swath of damage through there, so it touched down somewhere over the lake. Well, Branson, so we're seeing this thing, and Branson's over here, and you can kind of just follow it right into, there's downtown Branson right there. You can follow it all the way through along the strip there, and then it goes even east of Branson, across Taneycomo, out towards just south of Forsyth, and then out in the central Taney County woods right there is where we started to lose it. It's pretty wooded in there. We had a guy, one of our pilots, volunteer pilots that we use, Mark Ingram. He's a United Airlines pilot. Some of you guys may know him. He's out of Purdy, Missouri. We couldn't get, the woods are so thick out there, we couldn't find the endpoint, so we had him fly it, and he gave us the endpoint there of that Branson tornado.
So some of those other slides back around, they showed the debris up in the clouds. Does that still necessarily mean there was something on the ground, or was it just being carried along still?
Yeah, and that's a good question, and that's the dilemma that we have, especially with the TV people, because when we see these things, the tornado may be already dissipated. If it's only a brief touchdown, the tornado may be dissipated, but that debris is still flying in the air. So you're exactly right. That's something we have to consider. Okay, so we're talking about more tornadoes than what we realize had happened. Well, check out this a bit. This was October 13th, 2012. We had, there's Springfield, there's a radar here. We had this line segment come in. And we started picking up a tornado here, picked up one here. And the reason why we're diagnosing these as tornadoes is because they're associated with velocity couplets. That's part of the criteria in diagnosing these things. They've got to be associated with either some type of velocity shear or some type of velocity couplet. So we've got two of them here. Still got those two on the ground there in northeast Lawrence County. And here's a third one that pops up right here. Okay, again, and you can see each one of these has a velocity couplet. They're very weak, but they're there. So we go up time, one of them dissipates. You still got two of them on the ground. Oh, there's a third one. Still got three on the ground. And this is where I'm telling you that we're still seeing these things well into east of Halltown and towards the radar. And this one, see where the radar is, the cone of silence? Look how close that one is.
Wow.
That one hit part of Willard there. We actually went in there and surveyed that damage just on the south side of Willard. Right there, pretty close to where AB kind of curves right there into Willard. So we had, 5 or 6 tornadoes just with this weak-looking squall line that came through. It's pretty incredible.
So we don't need to be so complacent when they say, "Well, there's a slight chance." We need to be watching it.
Yeah. Well, the good thing is that these families of tornadoes, most of them are going to be very, very weak. So, unless you get directly hit by one of these things, you're probably going to be all right. They're just very small. Here's another situation. This was October 13th, 2014. So this was just this past October. And this doesn't look like anything, maybe some heavy rain, right? Yeah, that's all it is. Well, we verified a tornado right here, confirmed the EF0 with this little spec here. Notice it does have a velocity coupling. Gets a little bit stronger. Steve Runnels went out there, confirmed that it hit an outbuilding there, destroyed it. Okay, so we're going to go with time here. Oh, another one pops up there, northeast Lawrence County. Okay, that one's still going. We got another one that pops up there, crosses into Greene County there, just south of Ash Grove. Oh, there's a fourth one. Just northwest of Ash Grove, we did confirm that EF0 there, went out and saw we got the damage, a bunch of trees that are down. Okay, we'll go with time, that one begins to dissipate. Now we're going to go look up to the north as it's moving into Polk County and Dade, Cedar County. There's one right there, south of Fairplay. That gets a little bit stronger. There's a second one there. There's a third one that develops right there just east of Highway 13, south of Humansville. There's another one that pops up right there. That one goes away. But every one of these, we're sure those were tornadoes because we had this shear zone and these couplets that are developing with those. Again, this is the stuff that we took to the storms laboratory and down in Moreland. And those guys were like, well, the tornadoes, that's all it could be.
That was the one that hit early in the morning,
This was the one that hit early in the morning
and
last
the warnings
October.
had all been dropped on it, and,
We never issued a single tornado warning.
or even a thunderstorm warning until like, it was in Ash Grove or something.
Right.
I think there was a brief warning that popped up, yeah.
I mean, there was what, 8 or 9 tornadoes?
Yeah.
We didn't get a single one of them.
Wow.
It's pretty incredible.
You know, I really like the way that the new system works. I've been studying it. Dad used to work on radar systems. He'd be fascinated by this. He's not here anymore, but he'd be fascinated by this system because he used to repair and work on it. And to me, it's just awesome because a lot of the folks that used to say, well, the storm's dying down, I'll just go ahead and leave myself if I can and I'll leave. And behind them, we'd have storms pop up. I lived in Kansas for a long time. I moved out here 14 or 15 years ago now. I was a pilot, I float around. And I'm telling you, they're out there, like you said, you don't realize it. I just think this is just fascinating.
Well, and being critical of ourselves at the National Weather Service, how many times has a spotter called in, well, we've got a tornado? No, you don't. Well, gotta think about that now, you know, it makes you wonder. Or, you know, somebody calls in, yeah, what about my damage here? I had a tornado came through. No, you didn't.
All the
Maybe
arguments
you did.
over time where they had a tornado on the leading edge of a squall line. You can't have one there.
Yeah.
Well,
Remember that I called in? I said tornado just come behind me.
Yeah.
And everybody said, did you see it? No, but the train went by without the tracks. Yeah, and they couldn't see it on radar.
Okay, so this is important. When we see these tornado debris signatures, the TDSs, we're going to put that into our warnings and our warning statements. Okay, so here's a situation where we put it in here, it's a confirmed tornado. Okay, the source of that confirmation is radar. Okay, so we had to adjust how we're telling you these things. And then down here, they'll say tornado observed. So there's 3 different locations where we're going to tell you that it's a confirmed observed tornado by radar. Okay? If a TDS, a tornado debris signature, is identified, we're going to communicate that through NWS chat. Okay?
Pigeon,
Yes, sir. You got the count? Okay. If we're not exactly sure if it's a TDS, because some, you know, that data is noisy. It's noisy. There may be some situations where they look real weak and we're just, man, is that really one? We're not sure. We're still going to tell you that a radar is indicating a possible TDS. We're not confident that it's a true TDS. Therefore, any reports of damage from that area would be greatly appreciated. So this is the stuff that we're telling the news stations. We're depending on them and their broadcast and the reach that they have and their viewers to tell us about the damage so we can go out there and take a look at it and actually confirm that. Now, a little bit with that, the National Weather Service will only document tornadoes based off of real damage. Okay? The science is there, and there's no question about these things being tornadoes. But we need to find the damage. If we see one, we're going to go comb the area and see if we can find damage. If we can trees down, whatever it is. If we see one, we're going to try to notify somebody, the emergency management director, that may know that farmer, that rancher, that resident of the area that may have been hit. So see if we can get out there and take a look at that damage.
So this is where everything even kind of saying, location and everything else.
Yeah. Exactly right.
And this is what I was trying to query with Steve, that the spotter training, you know, you want me to focus on getting after the storms pass, getting those spotters into those questionable areas.
Yes, that'd be
Yes.
great. Now we get, an area somewhere else rural. If you got spotters, say, hey, go take a look at this area, see if you got some trees down or something. That information is huge to us, because then we can go out there the next day and verify it. Because we want to verify every single one of these things that pops up. It's important to the research. So every one of these that pops up, we want to see the damage.
I was going to say, has there been a documented case where the TDS has been observed, but no damage has been found because it is a debris signature?
Well-
It would lend to the, theory that if there is this signature on the radar, there must be damage
Right.
in this location.
Here's the deal. That has happened. These smaller tornadoes, if they happen in an open field and they're just throwing up leaves and they're not hitting anything, what's the evidence that it was there?
No ground scraping, nothing like
Right.
that.
The smaller tornadoes aren't going to scrape the ground.
Right.
Okay. Here's the other thing, the other problem that we have. This is why we have a group of pilots that will fly for us. If the road network doesn't allow us to get in there to see where the damage is. Say we had a brief touchdown or a touchdown that was maybe only in the ground for like a quarter mile. The road network may not allow us to get in there to see it. So that's the other problem again. So that's why we've got these group of pilots. We got about 6 of them. We're trying to spread them out across geographic areas that we can call on and say, hey, we saw one of these. It should be right here. If you get a chance, can you go fly that for us? And these guys, they do it for free, and they want to do it. They want the assignment. They want to see where the damage is.
We did that in Iowa with
The thing you watch for from the air too is, I fly this, I used to fly this all the time. Thing you watch for from the air, even if you can't see the trees are twisted, if they have a crop in the field, it lays crops down different from rotation than it does from a straight line wind.
Yep.
So you can tell what it was.
Yeah, you're exactly right. Or it'll mangle up trees differently.
That's right. You can actually see the trees the way they went down.
Okay. So remember, so far there have been 25 official tornadoes without a TDS. So tornadoes that have happened without being able to see the TDS. So it's important for you guys to know that the lack of a TDS doesn't mean there's not a tornado there. The science just isn't perfect. The technology's not perfect. Maybe one day it'll get better. It probably won't though until we get a greater amount of radars that can see really well. But the way funding is, probably not. So this is why we still need you guys. We need the spotters. Very important to us. Real quick, I just kind of want to go over a couple of different storm types. The supercell, we've got the rotating updraft, which is why we have the hook echo that forms there. And a lot of you guys know that this would be the heavy rain section of the thunderstorm where the straight line winds would be. The possible hail would be closer to that updraft, but the tornado region with these types of storms is going to be right there at the tip of that hook. So as spotters, you want to try to get into this region here, south of that hook or southeast of that hook, so you can see in that tornado. And I just wanted to kind of point out, overlaying the velocity of this storm here, just to kind of show you that the strongest rotation is underneath that hook right there. Just to prove to you that that is where the tornadoes develop within these supercells. So if you see these things come into the Springfield area, Greene County, wherever you got spot, you kind of want to be on the southeast part of those storms if they're moving northeast. The problem is sometimes they can kind of veer to the southeast, and that's when you got to be nimble as a spotter and make a decision to get out of the path. Joplin supercell, same thing. This one wasn't quite as isolated though. You can make out the supercell and the hook echo right here. The problem with this one was you had a cell that was merging into that tornado as it was going in. But I wanted to show you the velocity, the Joplin supercell. Right in here is where that strong rotation is, and that's the tip of the hook right there. Would have loved, the dual pole technology got in place about 9 months too late before we were able to see. I would have liked to have seen the Joplin tornado, but the technology wasn't quite there yet. Okay, I want to wrap this up here because we've talked a lot about squall lines tonight and their ability to produce these smaller tornadoes. Sometimes they can produce, every once in a while they can produce an EF3. I think there's been a couple EF4s that these things have produced as well. Our office does a lot of research. We're probably groundbreaking, leading research on squall line tornadoes. We're looking at what the different reflectivity structures look like, because we just get so many of these squall line tornadoes in southern Missouri. And so we've got to, and they're hard. They're very hard to warn for. But this is a structure I want to introduce to you guys that we've never talked about in spotter classes before. You see this line segment right here. And notice this nub feature. It kind of sticks out on the leading edge of the squall line. Well, that was just to the east of Springfield about 4 years ago. And when that stuck out there, that's when I immediately got the tornado warning out without even looking at the velocity. Sure enough, right there in Webster County, we had a tornado. This is what we call, again, a nub feature. Show you another one of these, what these look like. Here's another line segment. You can see kind of this nub sticking out right here, front inflow notch right there. There's a tornado location right along this shear zone, this velocity shear zone. So
is that the one that hit in the trailer park there in Webster County east of Marshfield?
No, the one I just showed you is southwest of Marshall, just barely east of the Greene County line.
Oh.
So north of Rockersville.
Oh, okay.
This one right here is in Lincoln County, Tennessee, and you can kind of see this nub feature here. That one produced a kind of a long track tornado. The other structure I wanted to point out to you guys. The tornadoes don't always happen on the leading edge of these squall lines like we've always told you before, okay? Sometimes they happen on the back end of the squall line. So this is the super derecho of May 8th of 2009. And on that day, this is what we call leading stratiform structures, where the tornadoes are right there on the back end of the squall line. So this can kind of get you off guard because you've got all this rain. If you're chasing one of these or trying to spot one, you're dealing with all this rain, and then all of a sudden this thing pops up. Okay? These are very hard to see, if not impossible, because they're going to be rain wrapped. But these produce some pretty strong tornadoes that day during that super ratio. So again, tornadoes are not always going to be in the leading edge of these squall lines. Sometimes they happen back there towards the back. Here's another one right here, that same day, Dallas County. This one actually killed a guy up there, I think right around Charity. But again, this one was on the back end. We missed this one. We didn't even issue tornado warnings on that one. This happened. We weren't even familiar with this type of structure of a thunderstorm, and the radar operators didn't get a lot of these. But we're learning more and more about them, and the research is really good here locally here at the Springfield office. Here's another structure with squall lines here. This is what we call a coupled inflow notch. You can see this storm has a front inflow notch right here. And it's also got a rear inflow notch. And in between them, that's where your tornadoes are developing. So this is another structure of a line segment thunderstorm that we're seeing that produces tornadoes very frequently. And you can see the reflectivity couplets that goes along with those tornadoes there. Another one of those, this is a Lincoln County, Tennessee, again, front inflow notch here, rear inflow notch, tornadoes right in between those. And you can see it right here in the velocity. All right, that's going to be it, guys. Any questions? Sir?
Does your computer equipment tell you where the highest speed is, or how do you know where to look? You just have to scan the whole display?
So you mean like what do you mean the high speed?
Well, I mean, is your workday sitting there 8 hours looking at a map to see something that looks like it's gonna be a tornado?
Oh,
Or
well,
you have something that alerts you that
so-
you got 80-mile-an-hour winds. You better start watching.
no, we gotta be watching those because the algorithms aren't going to point out every little single thing. I mean, it takes a human being to be able to catch these things, especially with the squall line stuff that I just talked about. There's not a single algorithm electronic that's going to tell you these squall line tornadoes being produced. And so with the TDSs, the tornado degree signatures, the radar's ability to see the tornadoes, there's not an algorithm that's catching these. Will there be in the future? Maybe. But right now there's not. So it still takes a human, a warning meteorologist to get those. That's a good question. Sir,
Are you sorry?
this is my son, by the way. What did you say,
Are
Lee?
you sorry?
Am I a spotter? No, after I about got hit by that big tornado, I don't do that anymore. I'll let these guys are a lot braver than me. I like to down on them.
As new TDS technology, is this being installed or deployed across the whole country?
Yes, sir. It is. It is. By the end of 2012, it was on every single radar.
Great, because I drive a truck across country. I use the National Weather Service warnings and a couple of different radar apps. And I find them absolutely invaluable to me. Keep from getting blown off the road.
Yeah. Yeah, especially when you're on these interstates, like a Kansas Turnpike or something like that. You've got nowhere to turn around. I mean, if you're on that thing, you're on.
I have seen personally so many tornadoes. It's crazy. You wouldn't believe the stories. I've seen one up here across Highway 13. I was going north on Highway 13 across the road in front of me.
Mhm.
See another one out in Holy Creek, Amarillo, Texas. Down Vernon, Illinois. That one blew my truck backwards 6 feet out into the interstate. And I had to stop because he was watching the radar and warning, and I knew it was coming at me, so I stopped. And it was close.
Yeah, yes, sir.
Are you familiar with the City website and out of Kansas?
The what?
City Whips?
No, sir.
It's a radar, conglomerate website.
Okay.
Basically, it takes all your different, you can go down to local level, local office level, or, broad spectrum with mesoscale discussions and outlooks, vorticities and all that.
Yeah.
I should know if you were familiar with it.
I'm not the best person to ask about web stuff because when I'm out of work, I just, and I don't intentionally do this, but I separate myself away from weather because it keeps a balance in my life. You can ask about who live here. I just really don't look at weather much. I'd rather look at financial stuff or something.
Yeah, it's really discovered tornado in the squall line. So we see any patterns that we've used
The squall line?
Yeah.
Yeah, I just showed you 3 of them. I just showed you 3 of them that we've identified. Three different patterns.
Three different consistent patterns in different squall lines.
That are producing tornadoes.
That we can use to strategize how we place ourselves.
Yes, and that's another course. That's a different course for you guys. But I did give you a little taste of it there. The nubs, double inflow notches, and the mini stratiforms, where the tornadoes are developing from the end. Those are 3 very consistent patterns that most of the country, if not just about any other office, they're not understanding that. That's the local research is where we're seeing
It's not long enough for us to adjust our position.
Well, it's a little harder because these squall lines are evolving so quickly over time that it's, you get a big supercell coming in, you can adjust quick. These squall lines are so messy. But I still think there's some use for spotters to show. I can come back and give you class on these patterns that we're seeing with those. So that's also some groundbreaking research. And you wouldn't be able to see those patterns given the old resolution of the radar. But with the super res, we're seeing it. So this is why it's new to us.
that we need to actually get a class put together of that. I mean, I don't like that.
We may need to, consider that in the future. We'll have another time for that.
Got a bunch of them I can show you.
Remember the last big one that hit the speaker campus, come out and come down through El Dorado and that way up through there? That's been 12 years ago, 14, no.
Oh, that was same day you made more.
Yeah, I chased it all the way from El Dorado up through there.
Yeah.
That was a big storm. But like we are showing here, the smaller storms we used to, we get people who call us all the time to talk to us and go, well, what do you think of that cloud? And I say, oh, I look like grass, you know? But because we usually have nothing in these small like storms.
Right.
But now we know that there is lots of something.
Right. Yes, sir.
I may have misunderstood you. You say, there could be debris thousands of feet up in the tornado mat of the ground.
Yeah, so
So how will this get up there if it doesn't? Where does debris come from? Off the ground?
right. Yeah, so like the very first one, TDS that I showed you, where the radar seen a tornado, for instance, in that example, we know it hit Turkey Barn. In that sheet metal, within a 5-minute time frame, it may have been even less than 5 minutes, but it was 5 minutes or less. That sheet metal from that turkey barn went from the ground up to 10,000 feet within a matter of 5 minutes. So that gives you an idea of the vertical velocities that are in those tornadoes.
So, but the tornado didn't hit the ground.
The tornado did hit the ground, it hit the turkey barn and threw that sheet metal up 10,000 feet.
Can you have debris up there without it touching the ground?
No.
Okay.
So that's so with those weaker ones, that's how we know those are tornadoes. There's no other weather phenomenon that can create that.
He's saying changes in the air much longer than the tornadoes on the ground.
Yeah.
Oh, is that what you're referring to?
I was thinking something about, I wasn't sure, you had tornado way up here, and somehow or other the debris from the ground.
He's thinking tornadoes at 30,000.
Or are these tornadoes hitting the ground and sucking stuff?
Yeah, so what we've got to be careful of is the, okay, so the tornado comes down, it tears up the debris, it sucks it up. Okay. Well, the tornado will dissipate before the debris comes down a lot of times. So the radar is still seeing this signature even though the tornado's already dissipated. So we'll continue to see that debris in the air even after the tornado's already gone. And then eventually it just comes down somewhere. Yeah, that's a good question. And that's an important question. That was one of the most important things that I had to get across to the TV meteorologists. Because we can't have them on air saying, yeah, I've got this tornado, we know it's coming right through Wheeler, it's blasting through Wheeler. Well, what if it's dissipated before it got there? They have to be careful with their communication.
This debris that the radar's reading, I'm assuming the heavier stuff comes out faster than the lighter stuff.
Yeah, probably.
So, what size debris is seeable by the radar before it dissipates the plane kicks it?
Pretty much all of it. It's going to, if you see like on a night where you've got all this clutter around the radar, all that is just very tiny bugs and dust particles. And, we can see pretty much all debris. I can see how fast you're going down I-44. We do that all the time. We're clocking cars. There's a piece on I-44. Yes, sir.
And bats.
When a tornado dissipates, is there still rotation that's not part of the tornado that's still up, that's pushing that debris up into the atmosphere?
I think so.
And that's why it takes so long for all the debris to come back down, because it's still within the rotation of the storm, even though the tornadoes technically died.
And that explains why, you have a tornado comes through Pitcher, Oklahoma, and we got debris over here in Springfield from it. That kind of explains that. Sir.
Have you ever put a camera on a pin and you're able to look on your computer and you threw the pin into a tornado? Will you ever find that pin again, or will the camera break?
The camera will probably break because of the debris hitting it, but somebody may find the pin. It just may not be you. That's a good question. Any other questions?
Google's drones might someday find one and get sucked up in.
There you go. I'm sure we'll see that someday.
On the dual pole, what is you're actually seeing on dual pole radar? What's the actual, like, you're seeing reflectivity on one, you're seeing the velocity, what's the actual
Cheap drones,
that you're seeing on there?
getting the
At
tornado.
least the breeze sensor, but what's that actually indicating on all that noise and?
Oh, yeah, that's, so you're talking about all the other noise.
Yeah, what's that actually, see, what's that bouncing around?
Yeah, and there's about 7 different things that can create that noise. And I had to go through all 7 of those with the TV Mets. I'm not going to go through all 7 here, but I can. There's storm gradients and things that can create that noise. Yeah.
Thank you very much.
Yeah. Thanks, guys. Thanks for
Thank you so much, Doug. We appreciate